Hello.
Have you met Gregor before, Jan?
No, I don't think so.
No, I don't think so
Okay.
either.
Okay. Hi,
Okay,
Gregor.
Hi, good to see you.
Yeah.
So Jan is a great expert in Agda.
That's great.
So,
I'm in the process of learning Agda.
Oh, that's great.
Yeah, I love it so far, but there's lots to learn still.
But do you have
Right.
experience with other proof systems?
Well, so I did work through this Cock in a Hurry and also the Lean tutorial, but I don't have extensional experience. For Agda, I worked through the whole of the PLFA, Programming Language Foundations in Agda book by Wadler. And that is very good, that book. So that is about the extent of my experience.
Okay. Well, that's great, I think.
Yeah,
That's really good. That'll be very helpful. So, I just want to we are streaming, so I just warn you.
well, that's
Yes,
a good
okay.
introduction to our audience.
Yeah, I don't want to. Yeah, just but yeah, maybe Jan, do you want to introduce yourself?
Sure.
Yeah, just like you were going to talk to Gregor like a normal person, like not on a stream. But just
Okay.
with knowing you are on a stream, so that you don't say anything you don't want to say.
Sure. Well, so my background is in computer science, but I also did a master's in logic. And well, I did that because I got really interested in logic because of Agda, precisely. Through Agda, I realized that proving stuff can be fun. And then, well, I did try to formalize some mathematics in Agda. But, well, eventually when I switched to, from research to industry, I ended up being a compilers engineer. So that is my job. I'm working with Paul in a programming language called Jubix. That, well, it's a functional programming language, and maybe someday it will have dependent types. So yeah, we are taking also inspiration from Agda and from Lean, and I'm hoping to learn something new today here.
Cool. Yeah, so today we're I have no Agda experience, and yeah, we've just been using Lean, and but we're gonna look at this paper by Conal Elliott because it's quite readable and actually aligns perfectly with the project we're doing anyway. And this way we get to look how someone else does these proofs in Agda, try to redo them in Lean, and compare kind of the two languages. See, is it harder to prove things in Lean or Agda, or is it kind of the same, or is there fundamental differences that make it theoretically different? Yeah. So yeah, Paul is the magic person who has found a way to set up both Agda and Lean without too much trouble.
Yeah, it was okay in the end.
Okay, cool.
We have, yeah. So we did start reading this last week.
Yeah.
And like you say,
just to make sure it won't be too.
Yes.
Yeah. But
I think we said where we get to co-induction by simulation, this may be a limitation of Lean.
Yeah.
But we might not.
But at the start, the first half of the paper, we don't have this problem.
Exactly. So how should we start?
I think we can go to the first definition. If you scroll down a bit, there's a.
Yeah. So shall I go to this in Agda?
Yeah, this one. Yeah. I think.
Maybe.
Yeah.
So now I forget how we can find stuff. Because we had some scheme right last time.
Oh yeah,
about
we
how
had a good scheme.
So this, I'm just going to predicate because I
Oh wait, yeah,
languages
yeah.
as type level predicates.
We had the tag file, the main tag file,
Oh right, okay.
and then whenever there was a figure, this was usually importing some code.
Paper tech. Right, so we need to go
Yeah.
here, and then we need to find
So figure one. So the first figure.
one.
So we can just search for figure. Or yeah, the
Big
first one.
big ref.
Yeah. So
Big language examples. No, I've gone too far. No,
I
language
think you
as
went too
type
far.
level predicates.
That looks better. Yeah, that's the one.
Lang ops.
So you see lang ops is the thing that's imported.
Yes, so I need to go to lang ops, I think.
It's
No.
probably language.
But what was the mapping? I forget now. Because it's saying here lang ops.
Yeah.
And the file wasn't called lang ops?
No.
So basically, this is the tech file, just to explain. This is the tech file that the paper is compiled from, and it embeds Agda code snippets. So it compiles these literate Agda files, and so it can type check the whole thing, and then embeds the code in the actual paper. But I don't see that.
If we can just open language, I just want to see.
Oh, and maybe it was maybe I have to search the project for lang ops.
Yeah.
Rather than the file. There we go. So it's in these like angle brackety things.
Yeah. There we go.
So here we go. Right. So you have this very weird. That all of this stuff is being ignored by the compiler, but this stuff is not being ignored by the compiler.
Yeah. Anything
So
anything between. If there's a begin and end code, that's picked up by the compiler, and everything else is ignored and assumed to be tag. But then also the tag, the paper thing that includes as like a special preprocessor which finds these things that are embedded between lang of like a thingy star.
Yes.
Like, and then it pastes that into the paper. So it's like two processors. Like,
yes.
but so here. So the first line is line 42, right?
Mm-hmm.
So this is
defining a language as a predicate, I guess.
Yeah. So A star is a list of A's, I'm going to say, and maybe that's not correct, but it's correct for a large part of the paper. Later this is abstracted again, and then set L, as far as I understand, L is just the universe level, so we can pretty much ignore it until at least the second part of the paper. And then set is not coq set. What set is in coq? I think it is prop in lean.
Right. Maybe you can go to.
Isn't set just a type, and L is the level? So the level in the hierarchy of types.
Okay, so it's not prop because prop is a thing in Agda that I didn't know about. Okay, and ace. So ace set, maybe that is set in coq. And so maybe set is just type. So maybe we just have something from a list of A's to type.
Yeah, I haven't seen S set before. But set I know
Totally
is a
confined.
type.
Okay, S is just type. Okay, that's very good to know.
Oh, look.
Okay,
Go to
great.
definition is wonderful. We didn't have go to definition last time. So it is just list.
Okay. But
it's made to
but
look
it's
fancy.
also set to set.
Oh, but it's a list that so this is like, as far as I understand it, it's like a normal list.
Sorry.
Yeah. So it's a list of some type, but the type appears on the left instead of the right. It's like,
Okay.
Agda is wonderful. So you can do this. So yeah, that answers that question. It's just list.
Yeah, that's very helpful. Also, what's interesting here is this is not an inductive type. Like I would have declared it. This is just a definition, like lang is equal to. It's just a type that is a function that goes from yeah. Like if you look at the definitional, like the equalities below as well, it doesn't, well, maybe I'm wrong, but it doesn't seem to be an inductive type, which I was expecting it to be. It's just equalities.
I think here it's defining the type of languages. So a language could be any inductive type that's indexed by a list of A's.
So is this an inductive, like on line 53, what is happening here?
Line 53. I was looking at 42.
Yeah, 42 and 53, those two lines. What is happening?
Well, what's W?
Could it be just a normal W? Yes, it's just
a variable.
Yes.
Well, is it declared ever?
Doesn't appear. It's not going. I'm going to definition. It's not going anywhere.
Okay.
So now I'm confused. Now if I look back at the paper, so type level predicate. So isn't this defining? Aren't these defining? On these defining doesn't this like symbol have type lang, and this is how it's being defined?
Yeah, so as I understand it, this empty set, or is it a phi? I don't know. Phi W is false or bottom, is a pattern match, and then the type is inferred. This is how.
Yes. Yeah. So this is this. So how do we ask what the type of this symbol is? Can we do that? Agda type.
W
goal
is
type.
is a list of
infer type,
right?
Yeah, infer type, and then you type that symbol, that phi or empty set or what it is.
You just said type that symbol.
Yeah.
But copy paste the. I don't know how to type that thing.
No, I think you can do like just like backslash and then
something. Yeah. Oh yeah, you have to describe char. Describe char. / empty set. Okay.
Yeah.
But I probably can't do that in the
mini buffer. It won't work.
It won't work. Okay, so I can copy paste in the mini buffer, can I?
Yes.
Okay, good. Infer to infer type. Oh, for this command. Oh, that's a goal.
Try infer top level.
Yeah, infer top level. Okay, great.
Hey,
oh, there it is.
There it is.
There we go.
Well, what does that tell us? This is just gubbins, is it? So it actually has type lang, but these are some constraints.
It's a parameter.
Yes. So it has 2 parameters, right?
Right. Yes.
So W is a set. According to this type signature.
Yeah, so that's not what I was expecting. I was expecting W to be of type list of A.
Yeah.
Okay.
And then this bottom, this is the empty type, or is it something else?
Yeah.
Misc Agda. No, it's bottom prime,
Okay.
which is data empty polymorphic
Okay.
with a renaming.
Okay.
That's very curious. I'm sure there's a reason why, but maybe because of this inference. I don't know.
Yeah, that's quite curious.
Okay, so this is not what I was expecting then. I thought these were definitions of,
Yeah.
like you say, pattern matching.
So wait, like, so Lang takes a list. Oh, okay.
Maybe
No.
can I do the
I'm
same
back.
trick
I'm back.
with Lang? Lang. Right, so Lang is a level set. No, this doesn't make sense to me.
Yeah. So it needs to get an A as well, right? The type parameter A.
It has a type. Yes. So it needs an A.
Yeah.
And then it gives us a type, a function type, which is in this thing. It's in the suck of L1.
Yeah.
So it like raises the type to a higher level universe, basically.
Yeah.
Okay.
But L1 is L, right?
Yes. It's done this unification here, I think.
Yeah.
So I think these are just definitions of languages. I hope so anyway.
Yeah, but it's interesting that it's not an inductive type. And it's just like these loose functions.
Yes.
Am I reading this correctly? Like,
so, Paul, can we try another type signature for this and say empty set is a language and see if it still type checks?
Yeah. Right. So copy.
Okay, let's see what happens.
This?
Yes.
Duplicate definition of. It must already have a definition. It must already have a type signature somewhere. That's what it's telling me, is it?
Yeah.
So I need to search for this. There it is.
Okay.
Okay, we got there.
Mm.
So indeed, it does have type. They are Lang.
Mm-hmm.
And then it does have type suck L. Interesting, because we were looking for where this was relevant last week, and it's already here.
Yes, and it would be interesting to know the reasoning behind, what basically Walter said. Why is this not an inductive type? Like, what's the reasoning behind that? I'm not sure.
So perhaps this is not actually, these are not used anywhere in the project, and this is just merely for the typesetting. Because they are, we do get more definitions of languages later, don't we? Anyway, we'll
okay,
see.
yeah, let's see
Right.
in the paper if we do. Like,
so we get languages type level predicates. I was going to say. Yeah, this is something we didn't comment on last week, was the well, let me just skip ahead to the next page. We can come back and no, it looks like not.
yeah, I think that's it.
That's it. Okay, so we are in this world where these are just functions, they're not constructors.
There is figure 5.
Okay, figure 5. Which figure 4? Yeah, figure 5, and then we have this lower.
Yeah,
a tilted square Lang.
Yeah. Tilted square. I think it's
okay.
Diamond. Is it diamond?
Okay. Diamond with a dot in the middle. Lang.
Yeah.
So this is a inductive version of it.
Shiny diamond. Maybe that's
Well, now we got the thing. We can see what it's actually called in Unicode. So what was the point? So we define all this stuff. We define all this stuff just as in terms of
functions,
and then we redefine it in terms of the inductive type. And then it makes a comment, doesn't it? That but these diamond ones are references to the previous section, are they? Something like that.
Yeah.
Well, I can't see where it mentions that now.
Okay, I'll find it.
We are referring to the original versions via the module prefix lower left diamond stub. So it says,
oh, it's in
consider the dual strategy of
4.3.
automatic. Yes. Language building vocabulary as functions on that data type. So 4.2 embodies the one choice of reflecting functions into a data representation. U and delta into a co-inductive data type of tries. Full patterns. Oh, hold on. I think I may have skipped too far. Is that right? Yeah, hold on. Yeah, sorry. Because this is the inductive one, and then it goes to co-induction, doesn't it?
Yeah, we want to start before that.
The symbolic differentiation style reflects language building vocabulary to an inductive data type. For convenience, use the same names as section 1 for these new counterparts and refer to the original versions via the module prefix. Diamond. So that's what I thought it was saying here, that this is actually, this is the new lang, the inductive type. It's indexed by the langs we had before.
Yeah, the diamond is the old thing.
And this is actually the function that we were just talking about.
Yeah, so diamond lang is the original lang.
Yes.
So you have to imagine that you read the paper up to here and everything was lang. And you got here and it's like, okay, but actually I want to redefine lang. So I'm going to refer to old lang as shiny diamond lang. And new lang will now just be lang. So that's what's going on here.
Yes.
So this function takes an old language and returns a new type.
Yeah.
So it's either, okay, yeah. And so it's a parameter for this type. The old language functions are a parameter for this type.
Yeah. You can have other. You can create other. These are the ones that you're allowed to have in this inductive type.
Yeah. So empty set is now a language parameterized by empty set. That makes sense. I would never thought of doing this.
So do you have an intuition? Learning something. Do you have an intuition for why he defined this language, this new language?
No, we need to go back and read because we misunderstood this last time.
Okay.
Because we always did it using the inductive type, and we glossed over the fact that there was this there was this thing. So maybe we need to go back and
Yeah, so that's already very interesting.
Yes.
Like, I would have started with the inductive type, and I would have never thought of like parameterizing the inductive type with.
I think what's nice about this encoding is that you then have in the type like the I guess the parsing function that encodes the language. Because if you define it from the start without the the index, in the language you just have language.
Yeah.
Right. So but you cannot reason in the type about the the parsing function. I think that could be the reason.
Yeah.
Yeah, good point.
Yeah, I think it's gonna have some very interesting results, like doing it this way. So okay.
Okay, so we try to do this in Lean without the inductive
let's
type.
try to do the functions in Lean, because I think we understand now what is happening. But
yeah, so this is like our previous, as you can see, our previous attempts at this. We don't. This is unindexed, like you're saying, Jan. I think it's a really insightful point. We just end up with regex here. So yeah, the types are not very interesting.
No. I think yeah, just make a new file.
Yes. I'll just put in here.
Yeah, that's not gonna. We can rename it like that.
What?
I just like there's so many langs, so that's not gonna get confusing at all. But yeah, let's not.
Oh well,
debate.
because I can't put Unicode. Maybe I can put Unicode.
Yeah, but let's not debate naming now, please. Sorry.
Now you see all of my Lean knowledge has just gone out of my head. So how can I define a type?
So
can I just do this?
Is it
or do I need to say type? I can't basically I can't remember anything.
Yeah, that's fine. That's fine. Let's go look at some. So we can declare a type with inductive.
Yes, but I need to, basically it's just a type alias that I want to define.
Maybe that's just diff, I think.
Yeah, of course. So it goes from list. I'm going to say alpha.
Yeah.
To type, something like this.
I think with type you can add a universe if you want. You can add a L there, or well, we use a U probably.
Okay.
Yeah. And then
I need to probably do some imports and from droppings, right?
Yeah, actually.
Oh, hold on a minute. No, this is the body.
Yeah. So I have on line 19, you can see the actual type in the Agda.
Right.
So it's just type.
So let's just leave it as type.
Yeah, and we can do okay for now, yeah. And then we need to define it.
Yes.
So yeah. And now we go back to line 42. And now we say
it's a function type list of a type.
Yeah. And we can make alpha what do you call implicit parameter to lang. To
Right.
there. Yeah.
I can say
Alpha type. Arrow.
Should an alpha be part of the body? It is. Maybe it's me that I'm not familiar with Lean syntax.
yeah. So I need to make this argument here.
No. We don't want it there. We don't want it there.
Like this.
We don't want to parameterize it. So, and then
Yeah. So the alpha colon type should be after the colon equal, I think.
It's part of the type.
yeah, I think it is still part of the type.
But it wasn't in the
bound.
it wasn't in the Agda code. No?
Yeah, maybe you're right. Yeah.
Like this.
With the arrow.
Yeah, with the arrow. And then
Remove this. Type mismatch.
yeah, cool. So now we need the universe.
Right, so we need the universe. So this one is
This is just
u
U
plus 1.
Oh, U plus
This one is u. This one is u.
Yeah.
And the u. This is u plus 1, is it? Okay.
Yeah.
Right.
We did it.
Right, so we do actually need the universe. We do need the universe annotations.
Yeah.
Okay.
Yeah.
So what happens if you put underscore instead of u plus 1? Is it
A good point.
no?
Oh, it tells me. Oh, it can't solve the universe constraint.
I see.
All right. Look good. But if I put Oh, I don't need to put it here, so maybe I was wrong about that. Oh, this is just type 0.
Yes.
Do we want it? We want it to be type 0, not type U.
I think it's U. I think. But we can check it with the Agda.
Because this thing. But what do we want this U to be the same as this one?
Yeah,
Yes.
I think we can check this with the Agda.
Yeah.
It might be the last one might be +1. That's what I'm gonna guess.
So set L.
Yeah.
So what is A?
So A.
Can we check?
A is
Yeah.
Yeah. So we did the infer top level.
We did infer thingy.
Can we just do that again?
Lang.
Yeah.
So it has L. I believe that's the A here. So it's L.
Yeah, but then the final one is
L plus 1.
Yeah.
Oh. I see. Okay, so we want L plus 1 here.
Apparently not.
No. You already have the +1 in the type of lang.
Yeah.
Okay.
So that's up here. That's here. Stuck L. And then this one here.
But yeah.
That's the type of lang. That's the that's the parameter, and that's the A that goes into the list.
But is this A defined as a variable somewhere in the Agda code? It must be.
It could be, couldn't it?
Yes, and there it will have a label.
Thank you.
Hey.
There we are. Thank you.
Yes. Okay.
Okay.
So we should have the U in the alpha. Yeah.
Okay. Thank you.
Cool. One down.
All right. So now we do empty set.
Yeah.
Of lang.
Yeah, I just need to define.
Oh, sorry.
This is not Jubix.
It's not Juvix. It's so close to Juvix. Oh my god, that's what's really messing me up here. We should need to. As I'm going to raise a bug tomorrow, we need to make it more different from Lean. Yeah. So what? So instead of this, we have. So how do we make this implicit? Because at the moment I have to provide it.
Why do you have
just
to provide it?
braces?
Braces.
Oh,
okay.
yeah.
Yeah.
Curly braces, yeah, like Gregor said.
Yeah, we don't want to. So here we just want, this is our W, so we put the W here. W list alpha. No?
No. So lang is already something that takes a list.
Right, but this has type, this is going to have type lang.
Yeah.
So I'm just expanding the type, this type. So this definition, I'm just expanding it.
Yeah, okay.
Because so lang,
yeah,
as far as I understand, is the type of the body.
Yeah. So we have to have a lambda inside.
Yes.
Okay.
We just have something that takes a W. Okay, how do you declare a lambda in Lean again?
Yeah.
I forgot.
We have surely,
no, maybe not this file. I don't think this file is going to help. I think it's fun.
Yeah, I need to bring up the. Oh, drat.
You
need to bring up the documentation, but it needs to be in Chrome because it doesn't work in Safari.
Yeah, I'm also searching. Sorry, I forgot. Yeah, it's fun.
We just put it over here.
Yeah, so I know how to do. Yeah, so you in parains.
Yeah.
Or maybe not this time. Maybe we can get away without fun. Then a parameter named W. Then equal, greater than. Equal, greater.
Oh, okay. Thank you. Yeah.
And then function body, which in this case will be bottom.
Yes. So how do we write bottom?
I think maybe it's capital false. I'm just gonna.
Yeah.
I'm gonna guess. No, I'm wrong. Okay. Jeez. Oh, there it is. Yeah, that's. Oh, it's a prop.
Empty.
And that's why it's redefined. In the
Agda. Empty.
Yeah. Okay. There we go. Yeah. So diff should be empty set because we're also gonna have empty string.
Yeah.
Yeah. Cool.
So what's the difference between this and then putting the argument here?
Because then you have something that takes a list and will return you something that takes a list and returns a type.
Right.
Yeah. Okay, copy paste, empty stir. Well, actually, no, it's universe first. We're actually having universal, which is.
I can't call it universe.
Universal.
Universal. Okay.
Yeah. So this is always true. So we need the opposite of empty.
We have an extra person in the room.
Oh wow!
Oh, it's connecting.
Hello.
Oh
no!
So close.
I'm going to go to true and then see what I should be using instead. Oh, not true. Sorry.
Yeah, true is what we want. Just the. Oh, That was so close. What happened? Like,
So empty has no constructors. Okay, that's we got to define this ourselves. Yeah, exactly. That's why we want to.
well, it's pretty easy to redefine. It's just annoying.
That's what I place on tie.
Is this a problem that this is a prop and not a type, or
Yes.
it should be the same?
Yeah, it has to be a type, not a prop.
So prop is this has sort 0.
So maybe it's unit instead of empty. It should be unit.
Ah, yes, yes. Good point. Thank you. P unit.
Maybe. But unit sounds right. Just yeah, unit is good.
It is also imported from data.unit.polymorphic in the Agda code.
Oh, good,
Okay.
good. That's a clear sign that we're on the right track.
Yeah.
Okay.
Oh, can I interrupt with a link question?
Yeah.
Yeah.
So why don't you need to import these empty and unit types?
Because I think there is an implicit prelude.
Yeah.
So
Okay.
there's implicit prelude, and then there's this. If you see this thing called STD, this is like an external dependency, and then there's something called mathlib, which is another.
Yeah. But
Yes.
I think
this comes from
implicit prelude.
How can I click that? I can't click on any of this stuff.
I think if you import list, maybe you can click.
Yeah. It's going to be lean dot something, isn't it? I think there's like a prelude thingy called lean.
I think you can maybe see,
and then it has all this stuff in it. But I think it's implicitly imported.
Got it. Yeah, thank you.
I think so, but this may or may be wrong information. There's just some stuff that's magically there.
Okay.
Yeah. Which can be confusing. So we're calling the what's the one called? Unit?
I know, I think you want empty the one, yeah. So this is empty string.
Okay.
So I would call this empty stir.
Yeah. So this one we take W. And then we've got open list, right? So we can hopefully say that. Oh, this is building equality, so I need
single equal. Yeah.
Oh no.
No. No. This is everything. This is we're getting flashbacks to Coq now. Because in Coq you have this prop and what is it called? Not type, but prop and something distinction. Which is it's completely different, I think, but it still was annoying. Okay, so I can click this and
no, maybe the Agda has some clues here because the double equal.
Oh, we can see what
will probably have the same. So they have a triple equal. See, so
this is the one with. Yeah, but isn't this just the normal built-in equality?
No, no. That's not the built-in equality. That's Well, I mean, it's not the equality that you use to define something. It's like
It's a redefinition of it
mm,
to be in set instead of. I'm sure their equality is also in prop. Like if you do a plain equal.
Right.
No,
Okay. Because this is, I think we're in the standard library now.
Yes. Well, kind
So
of.
this is the one. Oh, sorry, whatever it's called.
This is built. This is built in. You don't need the standard library for this. This is
Right. This is
yeah.
this is not part of the project. But then, what was the question? If I look at infer this type,
No equal
Single
doesn't
equals.
exist in Agda. Is a keyword.
right?
Built
Okay.
in. Okay.
So
Mm,
so what is the equivalent?
you can
then?
do. Can you infer what is 1 equal 1 in Agda? That should be prop, right?
What do you mean? 1 equals 1?
Mm.
oh, with the triple equality.
Just the plain equal.
Well,
Yeah, but plain equal is assignment. It doesn't mean the same
yeah.
thing.
It's set. So it's set. So a type.
Hello.
1 equals 1.
Hello.
Hi.
Hello.
We have a guest.
Yeah. Hi, Conal. We're just looking at your paper. We can't hear you. You're muted.
How about now?
We can hear
There
you
we
now.
go.
Fix it?
Yes.
Oh, super. Thanks.
Yeah. Welcome. Thank you so much for joining.
Thank you. Oh, yeah. Sure. I might not stay long, but I thought I'd at least say hi.
Yeah.
See
Thank
what
you.
you're up to.
Yeah.
Mhm.
Yeah.
Yeah. We already saw something interesting here. Yeah, we would have started usually defining the regex just as an inductive type, and you're defining it
Yes.
here as like just a sequence of functions, which is
Yeah.
already, and then using this as a parameter to the inductive type later, which is very
Yeah, I think that was
impressive.
one of my favorite insights about the exploration is that the derivative algorithm is not about regular expressions. I think Berzozowski thought it was, but I think it's not. It's about regular languages. And of course, they're closely related. And he talked about that difference. But yeah, but you could talk about it on languages rather than on that representation of languages. And then if you make that distinction, then you can use other representations. And that's what I did in the paper. I used two like kind of dual representations.
Yeah.
One of them is reasonably, you could think of as one of them is inductive, and that's regular expressions, but the other one is like the opposite. And
Yeah.
And the same kind of the same logic powers both of them, and they're essentially exactly identical algorithms, except one of them is the transpose of the other. It swaps the interpretation of the data type versus the operations on the data type. You do it one way, you get regular expressions, but the dual of that is tries.
Yeah.
Yeah, I don't think I've seen this approach of doing it on languages instead of on regular expressions, instead of like on grammars or something like that. But I think it's a much more natural, powerful, simple way to do
it. Yeah. We were also just looking at this, and like you defined the languages on type instead of on like prop, which we would have expected. Do you know why you did that?
Yeah, and that well, I think maybe my other favorite insight from this work is I think the essence of what parsing is came clear to me in this work. I mean, I thought about parsing for decades, but I think it never came clear to me. What's the essence of what it means to parse, as opposed to recognize a language? So there's language recognition and language parsing. I think Berzozowski, he chose regular expressions like one representation, but also a recognition instead of parsing. So to me, the difference between recognition and parsing is that parsing is proof-relevant recognition. I never had that clarity before I worked on this project.
Okay, hopefully I'll get there someday.
Yeah, so like for instance, an ambiguous language is one that for which some strings could be parsed in more than one way. That's what it means to be an ambiguous language, right?
Yeah.
So how do you talk about that? Well, you need, so how I did is I said it's proof relevant. So there are at least two different proofs that a string is in a language.
Oh,
Right.
All right. And so, and then I have a conjecture, which I would love to like look into more deeply with, slipped my mind with that. Let's see, I was talking about relevant language recognition. Oh yes, it's simply this. Everything that you could reasonably call parsing factors through proofs. In other words, like I think there's no general notion of parsing. There's no general precise notion of parsing out there other than the only one I know of is this one that I identified, which is saying it's proof relevant parsing. But you take all kinds of things that you might reasonably call parsing. My conjecture is every one of them factors through generate a proof and then interpret the proof. So step one, generate a proof in exactly this sense of proof. Step two is whatever you want. And what distinguishes the different things that are reasonably called parsing is what step two is, how you want to interpret the proof. Now, when I'm in practice, people don't make the proof and then interpret it. What I'm saying is you could factor what they do through generating proof. And the generating proof stage is always the same. And then what you do with that proof, that's what distinguishes different notions of parsing. So that's my conjecture.
okay. That's gonna take a while to sink in.
Yeah.
And then there's one place where I changed Berzhozowski algorithm. There's one place where if you try to if we're generating proofs, and for instance you want to distinguish different parsings of an ambiguous language, I changed one of his rules in a way that was necessary to make that be true.
Okay, that's good to know.
Yeah,
we'll watch out for that. Yeah, maybe you've made me, but yeah, maybe the others want to introduce themselves.
Yeah, I'd love to. Thanks.
Okay. Yeah, I'm Paul. So I've been working with Walter on this stuff for a while now. But I met Walter. Oh, how many years ago was it? Pre-pandemic, so that's
5 years ago.
4 times. So I started running a study group where we started learning about dependent types, and we read the little typer. Then we started learning about Coq, and then eventually looked at this regular expression stuff. Yeah, but my background's in mathematics, but I'm currently working at software engineer, as compiler engineer. Yeah.
And so I'm guessing your background, your interest in correctness. I mean, most software people.
So I come from
interested in correctness in any active sense. Yeah.
So
which is my background too. Yeah.
Proofs, and because when I started as a software engineer, I had no idea about dependent types or how the mathematics and you could prove things correct. So I went from mathematics, went into software engineering, then realized there's this connection between them, and it was kind of amazing that this thing existed. But then you find the problems with it, the ergonomics. There is a lot of software engineering yet to be solved in making it actually usable. So that's what hopefully I'll get to work on in the future.
Heck yeah, that's great, Paul. Thanks. How about you, Gregor?
I joined the two on this project of learning Lean and formalizing their previous work in Coq into Lean about a year ago, I think. And my experience with Agda is that I just read through that programming language foundations book in Agda by Wadler, which I really enjoyed. And currently I'm starting my master's in computer science. I also have a mathematics background. So I did my undergrad in bachelor's and honors degree in pure maths. And now I'm switching over to computer science. And I'm interested in all the theoretical stuff. So I will do category theory and which I also did a course in undergrad, but now more applied to computer science. And I will do I will use lots of Agda for my thesis. So I hope to learn a lot while working through this paper.
Cool, great, thank you. Thanks. So I want to put in one just like a suggestion, something to be sensitive to in school, but which is currently the sort of theoretically inclined, especially programming languages. People are into operational semantics, and most of PLFA is about that. Most of PLFA is because it's based on Bentley Pierce's book.
Yes.
PLF, right? Yeah, and that book is solidly in the operational semantics camp. What I've identified is that to me, what's really important is not just verified programming, but because every implementation is correct, right? I mean, you take any implementation, it's correct if you make it its own specification. Right?
Yeah.
Because then the specification it is itself, right? So it's like worthless. The idea of verification by itself is worthless if you don't have a good a specification. And what I've noticed is that operational semantics never gives a good specification. Where the specification is always complicated. It's always wrapped up in the definition of a language, which adds unnecessary complexity, and it's wrapped up in a mechanical notion of computation, rather than what something really means. It's some idea about how some abstract machine executes it. So for those two reasons, everything that's done in operational semantics is much more complex than it needs to be. And so almost all the work goes into just doing busy work, kind of bureaucratic stuff of like proving progress and preservation, all this kind of stuff that has nothing to do with computation itself. That only has to do with one view of languages and what they mean.
Yes.
So rather than something that you want to get computational insight into. So you'll almost certainly kind of be fed that in grad school. And I just want to suggest, like, carrying that little bit of that question in your mind of, do we have good specifications and what makes for good specification? I think good specification, the most important thing is it is simple and precise at the same time. So
I think
it's no good being simple if it's imprecise. It's no big good being precise if it isn't simple. It has to be both of those simultaneously. Yeah.
I think that is a very valid point. And so when looking at many of these progress and preservation proofs, it seems to involve lots of just copy-paste boilerplate. But exactly. I think it would be interesting to, it seems to be feasible to automate lots of that. And so that would be an interesting question to look further into.
You could automate it, but what does automation do? I mean, automation sort of hides awkwardness of proofs. What I think a much more worthy endeavor is to eliminate awkwardness in proofs. In other words, have genuinely simple theorems with genuinely simple proofs. Right? Because otherwise, you just have some closet you're sweeping all your kind of trash into. And the more hidden it is, the harder it is to improve. Right? I mean, it just as like sociologically and psychologically, you hide something, you're not going to improve it. So I'd say the opposite strategy. Don't automate. I mean, some automation, yeah, like ring solvers. Thank you. I don't want to do that myself. But other stuff, I really want to be visible so I can improve it. And I think Cock and Lean, because they lean so heavily on proof automation, they're really about hiding the kind of the unnecessary complexity rather than eliminating it.
Yeah, that's also what's interesting in this paper is the how simple the proofs are, and that's the part I'm most excited about understanding why. But Jan, do you also want to introduce?
Yes, I can introduce myself.
Thank you. I don't think I did scroll far enough. There we are. Hi.
Hi. So my background is in computer science, and then I started to get interested in Haskell. So I went to Chalmers for some time, and there I discovered Agda. And through Agda, I think I really learned what it meant to prove something, and I really enjoyed that process of learning. So I've kind of kept my love for Agda since then.
Yeah.
And then I studied some logic because I wanted to learn more about mathematics and its foundations. And after that, I used Agda to formalize a bit of mathematics. And finally, I ended up being a compiler engineer in the same team as Paul.
Wow. Cool. Thank you. Thanks for the introduction.
So Paul
Appreciate it.
Found Jan and technically Gregor is from Germany, right? And he
Yes.
went to South Africa to study more, and then that's how my professors know him. And then they were like, "Hey, do you want to like meet Walter?" And then we like, and that's how we
Good.
joined the group as well. So that's just to
Super.
show all the connections. And like I met Paul like the week I landed in London because of the study group he started.
Very nice.
Yeah.
Great. Huh. I could say a few words about myself. So I'm Conal. I live in California. I live out in the woods, and I've used Haskell for like more than 25 years as my main language, and then I switched to Agda about 4 years ago, 3.5, 4 years ago. And my reason for switching was I was mentoring a group of folks who were designing hardware for accelerated machine learning, and I had come up with a real clear compositional way to think about linear algebra that's different from matrices. It's just a lot more parallel friendly and a lot more logic reasoning friendly. And so I was mentoring them in the process of, if you're going to do some linear algebra in hardware, like understand linear algebra in a really clear way that helps you with both with correctness and with acceleration, particularly with parallelism. And I was doing that in Haskell, and I gave them the puzzle, what it means to do it correctly, in a really simple way, without saying anything about the implementation strategy. And I found they kept offering solutions that were incompatible with the specifications. So I have this very simple way to talk about specifications, which is that you have a meaning function, like a semantic function for representation. So like for matrices, a matrix represents a linear function. That's what matrices are all about. It's exactly what they're for. Matrices are about a representation of functions that are linear. So you could take any matrix and you could map it to a function and a proof of that function's linearity. And that's how you would say it in a kind of type theory way. You map it to a linear function, and then every operation on matrices has to correspond to an operation on linear functions, in the following sense. Like if you take composition of linear functions, you can ask the question, what's the operation you use to combine two matrices such that the meaning of the combination is the composition of the meanings? Okay, so that's what all my specifications look like. They're all homomorphisms. All homomorphic equations with one unknown, and here the unknown is what's this operation that you use to combine matrices, right? And the answer is multiplication, which shouldn't be called multiplication; it should be called composition, right? Because that's what it means. And if you look at it, and then addition, what operation denotes addition of linear functions? Well, that's the thing we call matrix addition. And that question explains why are matrix addition and multiplication so different. It's because multiplication isn't multiplication; it's composition, which is very different from addition. Right? And then if you want to know things about like is matrix multiplication associative, it has to be because function composition is associative. So you can kind of prove these things in a really easy way. So I noticed that they kept slipping back into like, what should this mean, or how should this work, or something. And I would say, no, remember the specification. It's homomorphic. The meaning function is homomorphic. That's the specification always for every kind of correctness problem. And I realized that I didn't enjoy like my role of reminding them, no, you forgot what the question was. And Haskell wasn't reminding them for me, and it couldn't because the type system wasn't expressive enough. So I realized if I switch to a type system that's expressive enough to really have correctness in it, then they will, every time they forget and they try something, they'll have a proof obligation, they'll fail to meet it. Right? And that experience, which is like right in their inner loop, it's like remember what the question is in their inner loop. That I think is a much more effective way for them to learn, and it's more fun for me too, mentoring them. So that was my main motivation to switch from, because I've been doing proofs of my Haskell programs for decades, but I wasn't taking advantage of it in the sense of like, people are still out there doing weird monadic stuff in Haskell and not realizing it doesn't mean anything mathematically. And you can never prove anything useful about it because it has no mathematical basis. And the Haskell community doesn't really understand the difference between mathematical Haskell, the thing we started out with, and this thing that's basically just kind of Fortran reincarnated in Haskell, this monadic IO stuff. the community doesn't recognize the fundamental difference. One is math and the other isn't. So one is we know what we're doing. The others we're just hacking like we were in Fortran and pretending we're not. So I wanted a way to raise the level of discourse so that people will have to be reminded of the difference between math, between well-founded programming and not well-founded programming. And I realized that Haskell just can't capture that important distinction. And the Haskell community is drifting further and further away from what we were about, which is practical correct programming. That's what we were about in the 80s, and then the Haskell community lost its way in the early 90s, and I think will never find its way back. And that's a difference that I find it's just too hard to get people to see. So I wanted a way to have the specifications be, precise and machine checkable.
How do you think the Haskell community drifted away specifically, or what was the trigger?
They got seduced by this thing called monadic I/O. I use this scare quotes because even the term is an expression of confusion. Like the idea that this I/O thing is a monad is not even false. It's a nonsensical statement.
Well,
because what it means to be a monad is you satisfy equational laws and equality is undefined on I/O. So it's kind of, it doesn't even get off the ground.
Well, if you think Haskell I/O is, you should see what Lean did with I/O, or with there's finally a reason to use the identity monad, and it's just to get the do notation that Lean gives you, which allows you to basically just do imperative programming with for loops and mutable variables and everything, but you end up with a pure function because it's just the identity monad, and it's pretty wild.
So I have one question,
and also it's very self-defeating because not only does this imperative stuff defeat correctness, even the ability to express correctness, because correctness is in terms of the meanings of things, and I has no meaning, so you can't even formulate good questions about correctness. But it also defeats performance, which is kind of the justification. One of the main justifications people use is they want performance, they want to do mutated things. But performance depends on parallelism, right? And mutation is antithetical to parallelism. It makes it too hard to be practical.
Yeah.
So it's just a lose-lose.
Good point. Jane?
Yeah, so even if you take the fragment without I/O of Haskell, it's still not expressive enough, right, to talk about correctness?
Yeah,
yeah,
exactly. It's not. Yeah.
So
and those two phenomena are related. Because Haskell isn't expressive enough to talk about correctness, people don't notice that I/O can't support correctness.
Mm-hmm.
Right? If you did this in Agda, right? Agda has correctness and it has this non-mathematical I/O. So you can at least try to prove things about it and fail. And that I think is really important, to try and fail, right? Because then you realize, well, something's wrong. What's wrong? And you think about it, and eventually kind of realize, oh, it's because it has no mathematical properties, because it's not a mathematical thing. So that's what Haskell lacks, is the ability to remind people and over that when they're programming with I/O, they're doing Fortran, not functional programming. They're doing imperative programming. And so all of our motivations for doing functional programming are going to fail. Well, most of our motivations for doing functional programming are going to fail.
Well,
anyway, that was my motivation for switching. Yeah.
No, that does make a lot of sense to me. I was for my honors project in my undergrad, I tried to prove something about a Haskell implementation using pure maths. And I realized what I did in that implementation was based on some nice mathematical ideas, but the implementation was a whole big mess in Haskell. So when I found out about Agda, I was very I really liked this idea that when you program something, that program is already the proof of of its own correctness, in a sense.
Yeah. Yeah, or it can be if you give it a descriptive enough type.
Yes, of course, yeah.
Which you can do in Agda. Yeah, that's a great thing. I don't know if you guys have noticed, if you poke around in the Agda standard library, the algebraic classes all have laws. That's great, except for monad, it doesn't.
Oh, okay.
Yeah, that's true.
Yeah, why is that? I think it's because everybody's favorite monad is not a monad. And if you include the laws, you have to find that out. It's a lie.
That is interesting. I've never like tried using any or doing any IO in Agda. So you still have that IO monad in Agda.
Phonad, yeah.
Okay.
Yeah.
Interesting.
Yeah. So
yeah, it's always funny.
I care about performance. I'm very like efficiency driven. So to me, it's like CPU is a non-starter, right? Like if you care about speed, you're not going to aim at the CPU, whether you program in C, Rust, or Haskell or Agda, because CPUs are phenomenally inefficient. Right? They have the von Neumann bottleneck. They have the interpretation bottleneck. They're incredibly inefficient. You can get like easily 1 to 10,000 performance improvement in where it matters, which is energy, by doing your own natively parallel computation. In other words, by doing hardware design. So that's one of my main interests, is doing correct hardware design, correct, sophisticated, efficient hardware design. And so like none of this IO stuff would help at all, right? Because it's completely the wrong model. I mean, it isn't a model at all. It kind of is in the neighborhood of a vague model of the von Neumann computing, right? But it's not really anything mathematically precise. But even if it were, it would be the wrong model. It would be a model that is sequential primarily, right? And no sequential foundation for computing can be efficient in this century, because efficiency depends on parallelism. CPUs are getting a little faster each year, right? In other words, single-threaded performance is getting a little bit faster, but parallel performance is getting enormously faster right now, because you're getting GPUs with more cores, you're getting FPGAs with bigger kind of more cells, you're getting ASICs. You could cram billions and billions of transistors into. Now, all that stuff is about parallelism. And also just for the fundamental reason that nature is parallel, right? We live in a parallel universe, and computers are parallel because they're made out of nature. They can't help but be parallel, but then they waste almost all of their effort pretending to be sequential.
But is Brzezowski's derivatives not sequential?
Is it?
It's operating one by one over a list, right? You have to do a fold, right? So it's an all folds kind of sequential.
Yeah. But some folds you can do in log time.
Okay. But this one?
Yeah. I don't know. I haven't considered it. But for instance, you can evaluate polynomials in log time. Log in the degree, right? You can do addition with the carry chain. That's a kind of sequential thing. You can actually do it in log time, despite the kind of obvious sequentiality. Every fold, if you can see how to reimagine it just a little bit, so that the binary operation is associative, then bam, it's log time instead of linear time. And how do you do that? By parallelism.
But
now this I've never considered. Does this one have any useful sense in which that fold is over a monoid? You get associativity.
Because that would be if you figure that out, it kind of changes the efficiency of a bunch of algorithms. Most of the internet.
I think if you and if you think in terms of regular expressions and this particular fold strategy, you're kind of already going towards some unnecessary commitments to how you represent it, and then how you evaluate it. Yeah. But if you think of the nature of language, and particularly concatenation, I think that's where the sequentiality, that's where the tug to sequentiality comes in parsing, is about concatenation.
Yes.
Right. It's because I want to parse the first language, and then I'm going to have a remainder string. I won't know what the remainder string is to hand to the second language. I'm done with the first one. Yeah. But that's just one strategy. And it's a sequential strategy. And in the age of parallelism, it's a very bad thing to assume. Right. I mean, it made sense.
Well, we do want to know that it's like at gmail.com, right? Like we need like
it has to be correct in the end.
For an email, like we need to know that the order is important. So we do need
absolutely, the order is important. Yeah, but is there an inevitable data dependency? That's the question between parsing the first half and second half.
I'm gonna say
a lot of times when it looks like there's it's maybe the answer is obviously yes, but perhaps actually no.
Yeah, I hope I'm wrong.
So like if you do a scan, right?
Yeah.
If you do a scan, so that's like a fold with all the intermediate results. That scan seems like the poster child for intrinsically sequential computations, right? Because each value is going to be each partial sum is the previous partial sum plus one more thing, right? That sounds like it's intrinsically sequential, but that problem actually is solved very nicely in parallel. It's just you got to be a little clever about it. And because you can solve that one problem in parallel, you can solve tons of other ones in parallel. Anything you can reduce to a scan, and there's a tremendous number of things that are surprisingly reducible to scan. So that's my favorite example of an obviously sequential but actually very parallel, and not just in kind of in theory parallel. It's implemented in hardware extremely efficiently.
Okay.
So, and that may or may not be relevant to this problem, but it probably is relevant to like maybe you shouldn't assume that there's an inevitable data dependency. Yeah.
So can I maybe ask something back to the paper here? So absolutely. I think you answered, but I didn't understand. Like the
oh sure, yeah, no problem.
So why did you, or I don't remember. Why did you define the, like if we go to Lang, right?
Yes.
Just in this file, like
this one
this
here
is on Sate, right?
Yep, right there.
Yeah. So on Sate and like instead of on prop, do you know why you did that? Was it important?
This was about the proof relevance. Because there's more than one.
Yeah.
More than one
way. Proof relevance is crucial.
Okay. Yeah.
Proof relevance is how you parse. Yeah. So that's the essence of parsing is proof relevance recognition. Yeah.
Okay.
Yeah. And I've never seen a kind of principled approach to parsing with Brzezowski's algorithm. In other words, anything that defines what does it mean to parse? Like recognition, we're all familiar with that. Recognition is, you could say, a set of strings. Right? Or I would say a function from strings to propositions, or to set. Yeah. But if you don't have proofs, what is parsing? Okay. And you could say, well, it's building some data structure. Okay, but what does it mean to build that data structure correctly? How do you even define the question of parsing? Recognition, it's a little easier. It's a sort of binary thing, right? Whether you use a Boolean or set or prop, right? You're talking about classifying. What if you want to know more than that? So I don't know any other nice definition, general simple definition of what it means to parse, not how to do it, but what the question is. Yeah.
Okay, no, that makes sense. I forgot. Yeah, I only forgot. Yeah. So I'm a bit worried here, just because
sure.
Like I think most people would assume the proofs were going to be on prop, right? And then so there's more infrastructure for this, like that's
so is that that's a lean thing? Like so Agda has set and prop, and most work is done in set. I've never actually used prop in Agda. So but lean and conc have this different orientation, right? Do they have proof relevant they do Curry Howard, right? Curry Howard's got to be in there somewhere.
Yeah, so we have
And
type.
Curry Howard is about proof relevance.
Yeah, we have type. Like
Yeah.
maybe Paul can even show the file we have at the moment in Lean.
Yeah.
Like we just started, but so yeah.
Okay.
So we have types, we have universes. Like
Gotcha.
Our U is your L, our set.
Yep.
Our type is your set, and yeah, the rest is just not Unicode. And
so originally we had like true here, which is the prop version of the. So if I go here, this is the one in prop.
Yeah.
And then we have empty, which is in type here.
Yeah.
Well, this was false instead of empty.
Oh, sorry. Yes.
Yeah. But yeah, same thing. We just have unit instead of. We have true instead of unit. But we have access to the other things. It all exists. It's just more of the infrastructure would be in prop because more people would be working in prop. So you would get more standard library automation in prop, I guess. And I'm just guessing. I don't know if that's true. But already here, like we're gonna have to redefine equal, right? Just like I think you have with triple equal. So yeah, we just need to.
This I can't even click here, but yeah, this will be on.
Prop. We're gonna need our own little macro rule. And
you're gonna need one in type instead of prop.
Yeah. So we'll lose some ring thing that we might need to go do, or like this, like which we might have gotten for free, right? Something like this.
Yeah,
this might happen.
Just okay, cool. Just a moment. I need to step away from this now.
Maybe it would be possible to transport the stuff from prop to type. I don't see how, but would be an interesting question to investigate.
Yeah.
I just want to get to eq. How can I get there?
So it's just like I think it will all be possible. It might just be slightly more awkward. So I
think the opposite is true in Agda. If you wanted to bring prop into Agda, you'd find like, oh, the algebraic classes are in set.
Yeah, so that's why I'm wondering.
So do you have a sense
it
like
is to be in type versus in prop?
Yeah.
That's
You would lose parsing.
Yeah. So you answered, So it seems to be important to the paper. So
I think it's super important, but then almost nobody else who plays with Brzezowski derivatives in a formal way, I don't think I've ever seen it.
No.
This question of parsing addressed, and Brzezowski did not address it. I had to figure out how to do parsing, and that there was exactly one of his rules was incorrect for proof relevance, and I correct it, I change it. And how did I know? Well, I had to make a proof, and I couldn't because it wasn't true. So I had to change his rule. Yeah, and it's his star rule. The rule for derivatives of star had to be changed to get proof isomorphism instead of just logical equivalence. Yeah. If I remember right, I think that's what it was.
Okay, cool. I'll definitely pay attention when I read that again. Because
you subtle thing.
You start reading these Brzezowski rules, you're just like, yeah. I've seen this. Like, like, why would anyone do it differently? Okay, so there's a reason. Yeah, cool.
So here's an example. If you, what is it? If you do A star star, so pick some character A and say A star star, that language.
Yeah.
Right? And then you can say how many parsings are there. Only many. You take like the empty string, right? Or even a string of a few A's. If there's one parsing, there's infinitely many.
Yeah.
And Brzezowski won't reveal that. His rule doesn't reveal it. It just reveals that yes, the empty string is in that language, but it doesn't say how many times they're in which different ways. And in general, it can't touch ambiguity of grammars. It can't notice them.
Yeah.
Would be true if you use prop. You won't be able to notice the idea of an ambiguous grammar.
Cool. Okay. So then it's worth the effort.
Yeah.
I just wanted to be sure. And then
So, but everybody else who's done formal work on this disagrees with me or hasn't noticed what I noticed or something. So
okay,
let's see.
It's worth it for this exercise.
Okay, good.
And then I think
why is proof irrelevant propositions the default in Coq and Lean? I don't. I mean, like, it seems to me Curry Howard is so profoundly important. Throw away the one-to-one correspondence, the proof isomorphisms. Seems like a huge loss, but I think I'm missing something because a lot of people are happy with that choice.
Well, I think it's because you actually want to run this code on like a CPU, not a nice thing. And so you want to throw away as much of the code that doesn't need to compile and just focus on the actual code that needs to compile. So you have like something in state or type, okay, you're gonna have to keep it. Something in prop, you can absolutely ignore it.
I see. So if you say propositions that never have content, that is proof propositions never have content, then it makes proof erasure easy. It makes irrelevance erasure easy.
Exactly. Like
a
no-brainer.
Whereas it makes a no-brainer. Okay, so instead of like tackling the question of how do we intelligently eliminate computation, we just make it easy, right? I mean, right? I mean, sometimes that's the right thing to do. Like, I have this hard problem, I have no idea how to solve it. I'm just going to make it go away.
Yeah. Yeah, and it does cause some awkwardness sometimes, especially with sigma types become quite tough.
Absolutely, yeah.
But or I've had lots
content is real important.
Yeah.
Yes. We've had lots of fun with that in Coq in the past. Yes.
Oh, so much. So many Stack Overflow questions. Can you explain this again? I just don't. And then the one problem I see in this paper that like will be interesting, like Coq has co-induction.
Yeah.
Lean is cheating at the moment. It used to have it, I think, in Lean 3. So it might get it again. But currently, like, there's been a huge effort to translate a lot of like the Lean 3 to Lean 4 in Mathlib. And if you look at the places where there used to be co-induction, they've found like little cheats around it. So that might be interesting.
Yeah, well, that'll wipe out half of the implementation possibilities, or not having co-induction, I think.
Yeah.
It's one of them's inductive, the other is co-inductive. On the other hand, so it's a trie. So that co-inductive representation is a trie over infinite strings.
Yeah.
Which was the original notion of a trie, except in type theory instead of set theory. And so because it's a trie, it's isomorphic to a function. That's what tries are, data structures that are isomorphic to functions. So you could represent it as a function instead, and then it wouldn't be co-inductive, and it would have the same semantic content. It wouldn't have, anything like the kind of performance implications, because there would be no caching or anything like that. But I don't think I did a very good job of, with that aspect.
No, that's not what this is about. Like,
yeah.
All right, cool. Okay, so then there's a way around this problem later.
I think so. Yeah.
Excellent. Okay, then.
Yeah.
Okay, so we're gonna have some awkwardness, but there shouldn't be any blockers. So that's very good.
I think so. Yeah. Yeah. Just use functions instead of tries.
Yeah. Easy. Cool. So I think, like, if anyone has any other questions, we can rather ask them. But otherwise, we can go ahead and try to redefine equal, or try to find the equal for type in Lean.
Yes.
Oh, I have a question for Conal, which is not related to parsing, but it's more general one. Yeah. So I would like to know your take about tactics. So for me, coming from Agda, when I switched to Coq, it felt awkward that I had one language for defining functions and then a completely different language for the proofs.
That's why I don't use Coq or Lean. I mean,
yes.
I just saw that. I thought, okay, you've got this lovely kind of functional Curry Howard gem, and then you throw some haphazardly designed imperative thing for programming on top of it. And that's why it was easy for me to dismiss
Okay.
Conk. And then when Lean came along, I looked and said, it's the same old stuff.
I think
So yeah, absolutely. Having there be one thing, and it's like Gary Howard isomorphism, and there is no difference between functional programming and proving.
Okay, so I think in Lean you have dependent pattern matching, so you can do a lot more Agda style, programming than in Cork. But I've talked to other people, and they tell me, well, if you want to do real math, you really need, tactics and automation. So my question to you is, do you counter that point, or what's your take on that?
It's what I said already. It's that when you hide things, you're not going to improve them. Right? So there's this wonderful book by James Glick. It's called The Information, and it's about the profound impact of the written word. Why the written word is so important. And he makes this point, which is that Homer, right? Homer's works came out of an oral tradition. Aristotle, right, and Pythagoras, those folks, they came out of a written tradition. So logic was birthed by the written word. Logic could not have come into being with an oral tradition. And why is that? And not just logic, but philosophy. Why is that? It's because when you write down an idea, it holds still, and you can look at it and reflect on it. And as more I reflect on it, I get more insight, and then I figure out what's a better idea. So being able to write down something and then reflect on it is like incredibly important. And tactics do the opposite. Tactics say, take your fuzzy idea, survive the process of getting something to work, and then hide it. And somebody else comes along and they look at your imperative recipe for reconstructing a proof, and they go, well, I don't know what's going on here. I'm just like eyes glazed. I'm just going to wait until something that's kind of human readable again. So I think the whole tradition of tactics solves a short-term pragmatic problem, which is, how do you get these nasty, ugly, hairy proofs out of my way? But they undermine the long-term benefit of let's learn how to do elegant compositional proofs, simple and enlightening. And to me, the most important thing in any kind of logical development, like this one you're doing, is in the proofs. It's not in the results, it's in the proofs. In other words, the proofs are what carry the insight, and the insight is what's valuable. Parsing regular languages is not valuable, not very valuable, but understanding proof structure, understanding the pattern, the logical patterns that undergird correct engineering, that's the thing of value. And so to me, it's incredibly important to put the proofs front and center and visible. Why? So that you can look at them, and either they're ugly and we're going to improve them, or they're beautiful, and the more we look at them, the more enlightened we get, right? And the more our thoughts are elevated, and the more we transfer our insights to other things. So I think the whole tradition of tactics is short-term gain and a long-term tragic loss. But what I'm not suggesting is just keep your ugly proofs visible. No, the point is improve them, and that's the point of the written word. That's why logic didn't come out of an oral tradition. And Conk and Lean are, in a way, this is exaggerating, a little colorful exaggeration, but in a way, Conk and Lean make proofs the most important thing into an oral tradition. And what I mean is it's an experience that kind of goes by as you're doing the proof, right? You're interacting with something, make the proof, but then it's gone, right? It's gone, and so you're like, okay, I'll just be satisfied with that and move on, and then do another ugly proof, and then hide it and move on, do another ugly proof. So my goal is that if we're going to scale up correct engineering, we're going to shift out of the dark ages of computation into the age of like science and reason, then we need to have proofs front and center, and we need to make them better and better and better. Which means, well, first of all, we need to make the theorems more and more elegant. That's why I encourage you away from operational semantics and language definition-based stuff. And then we need to make the proof process more enlightening and more easy. And we do that by looking at it, not by hiding it. So that's why, to me, it's with
that's very interesting.
Tactic-based thing, we're not getting anywhere.
because like
in a literal sense, the goal is like, I think maybe the Koch mindset is get the proof out of the way, like in a literal sense, right? It's hidden, but also in a like impatient sense, let's just get it out of the way and get on to the next thing. Yeah. And I think it is the one important thing, right? The proof.
Yeah, because like if I look at we've done some of these proofs in Koch before for derivatives for regular expressions, and they're very long. It took they're and when I look at your paper, they're relative, like very short comparatively and short-ish generally, I think.
Yeah, thanks. That was my goal.
So so I'm really excited to see like how you did that as we progress through the proofs, and like
we want to see where we went wrong with our approach.
Yes,
because our approach was not very elegant.
Good, thank you. Thanks.
And
I want to say too, I have such personally I have such strong distaste, like a visceral negative reaction to ugly stuff, that I didn't learn Koch, and I didn't really get into it because of because it's an awkward language based on ML rather than Haskell, when we kind of earlier when we were programming in such an awkward way, and then also the whole kind of tactic thing. Yeah. So because I have such a strong distaste, I haven't developed an intimate knowledge of it. So getting to work with you guys who are more familiar with it is helpful to me, and then I get to reality check some of my what's going on.
I really like the tactics. But I'm also interested to learn how to do the proofs more elegantly, like at the same time. But yeah, I can we have this whole we make our own tactics as well, just because it's fun.
Sure it is.
But yeah, it also saves a lot of trouble. Like there's lots of things we know is true. Lots of things about lists we know is true, and we just never want to think about it. Like it's just there's a list, just get it out of the way, just die. Die. It just there's a proof. I don't know the name, I don't care, just go away.
And you do this horrible thing in Koch where it's like you can just print out the proof that tactic is generated, and it's always horrible.
Horrible. Yeah, exactly. Yeah. And so you will never get the insight you would get out of seeing a beautiful proof and shaping a beautiful proof. Yeah, I think.
Yeah. So maybe this paper turns it around. But either way, I'm really excited to see the other side.
Good. Yeah. And then also the difference between derivatives of languages versus derivatives of regular expressions. That I think is a really important difference, and I think all the work I've seen works on a syntactic, what I call a syntactic or inductive representation, as if that were a language instead of one representation of a language.
When you say language, you mean list of A's to type? Is this what you mean?
Yeah. For like a recognition point of view, you could say a set of strings. That's what it is.
Yeah. Okay.
And then you could look at a regular expression. You could say, what language does the regular expression denote? Just like you would say with any language. What mathematical meanings does it denote? And then you can define that.
All our derivative work was also on a list of a list of characters. No, it wasn't A. Maybe it wasn't A, but strings to prop. So also.
Oh, you did do that. Oh, good.
Yeah.
Okay, so you didn't start with regular expressions.
No. We thought they were, but yes.
Gotcha.
But yeah, no. Paul had the definition there at the start, where it was it's
good. I'm glad.
Yeah, and it was kind of pretty, but it took. How many times did we redefine that?
Yes, that's why we kept redefining the same things and proving they were the same, in a big trying to find the right definitions that would make the proofs better. But
I do that too.
But we didn't make them as elegant as you did. That's the thing. We didn't get to we didn't get to very elegant things. But We were trying.
Yeah, we were trying. It was more elegant than where we started.
Yes.
Yeah,
We were
yeah.
keen.
That's what I do too. Yeah, definition. Then I know that the kind of central definition, like what is a language, right? That's going to affect everything. So any simplification I can make there, has huge effects down there. So yeah, I do that a lot. Go back and see, can I define this more simply?
Yeah.
Nice.
Any more questions?
Well, and not a question, just a remark on that thing, on that search for the most simple and most beautiful proof. I made this experience when trying to I'm in the process of trying to publish my honors project, which was this proof of I prove a part of my Haskell implementation, and I realized that what I handed in as my final project to get my degree, mathematically, well, it worked out all out, and I proved the properties, but then that I wanted to prove. But now when trying to rewrite it, I completely threw away all the definitions and realized I could just simplify everything so much, and I could probably still simplify things even further. So this process of revisiting over and over again the definitions, it is worth a lot also for getting insight into the essence of an idea.
Yeah,
that is something that
awesome.
I found out for myself.
Good for you. Good
so
for
I
you.
really get your point in in what you said. Yeah.
Super nice. Thanks.
Yeah.
Yeah, my grandmother was an author, and one of the things she taught was there's no such thing as good writing, only good rewriting. Right. I mean, you really got to be somehow tapped into the heart of the universe to get it right the first time. Yeah, it's in rewriting. Yeah. Yeah,
my grandmother is also an author.
Nice.
Yeah. Yeah, she's finally doing TV interviews, which is pretty scary to my family, because okay, we're streaming this. Can't say everything, but
yeah, you can't take this back. Yeah, it's out there.
But
no rewriting. Yeah, that's the problem.
Yeah, no rewriting
the interview.
But yeah, it is pretty scary. Yeah, she's got dementia, so, and now getting on stage and in TV situations is but yeah, she's finally getting a recognition for I don't know, 60 years of work. So it's
I'm glad to hear it, and I'm sorry about her dementia. That's really rough.
Yeah. It is, but yeah. She's still good at the moment. Yeah, she can still pull off a TV interview, so it's I think still going relatively well. Yeah.
Well, and now you write proofs, building on her writing of prose.
Yeah, there's some joke with the rewrite tactic here as well, right? I couldn't find it yet.
Yeah,
because that's the one tactic that Agda does have, right? You have rewrite.
That's great. Yeah. I mean, it's not the only one.
And ring, you mentioned.
Yeah, it's a ring solver. Yeah, that's.
I mean, it has some better programming.
Yeah. So there's I sympathize with wanting to use tactics. Yeah, and there are cases when I do, and I occasionally will use rewrite, and I'll use the ring solver at the drop of a hat. It's just it doesn't take much for me to do that one. So, and it's a little inconsistent with my reasoning about the value of seeing your proofs, but that's what I choose at this point.
And then you do also have like linear arithmetic or anything?
Oh, I don't know.
Okay. Okay.
Yeah. Another reason I chose Agda over Lean, even before I realized the dark side of tactics, the negative impact of tactics, long term, is that I know that Agda can grow good automation. There's nothing in the way, right? It's got a reflection API, and it's fairly nice. It's certainly better than Haskell's, than GHC's, I mean, which I use for compiling the categories.
Yeah.
So Agda can grow whatever automation you want, but Conc can never grow a good language because it is the language.
Well,
I mean, it's like it's kind of a decent language, but it's it is.
I mean,
what
this
it
is one of the problems with Conc. It's been growing since the 1980s or something. It's a monster language, yes.
It's a monster language, yeah. So
okay.
you can add new features to it, but there's something like fundamentally better, like to have simple, elegant, dependent pattern matching, kind of a thing. Like,
no,
I think it just wouldn't be Conc,
so,
right? Yeah.
Conc does, right? So like, okay, the original dependent pattern matching, it does have it. It's really hard to use, but they also have this thing that I like probably inherited from Agda called equations, which we haven't used. And this does allow you to write more readable pattern matching. So like the language is always growing. It can always grow into like C++ 21, where you only use if you only use these limited set of features.
If you only use them, yeah, maybe so. Yeah. Well, we will find out. We will find out. I don't like what I want to see. I want to see the prettiest Lean or Conc, I don't care, version of this language derivative stuff. The prettiest you can come up with, and I'm completely ill-equipped to do that.
Yeah. Oh, I look forward to doing that. Yeah, it's a fun challenge. So I hope everyone will join us. But like, everyone's got lives. But yeah.
Good.
Yeah, but yeah, that sounds fun. So yeah, we'll give it a go. But we might cheat and use a tactic here or there. Like,
I'll forgive you. and to me, the simplicity of proofs is not the most important thing. Simplicity of theorems is the most important thing to me by far.
Oh.
Simple proofs that's nice, but a machine is verifying my complex proof, right? So I might, by complex proof, I might not get very good insight out of it. As long as it's machine verified, I know it's absolutely true.
Yeah.
Right? No matter how complex, I know the theorem is true. But if the theorem is complex, for instance, if it's based on operational semantics, if the theorem is complex, right, then even though it's true, I might misapply it. So there's no machine assistance available for coping with complex theorems. Well, there is when you try to prove some other theorem, but if you go and try to apply them to some problem, right? So to me, because theorems, we eventually end up applying them with our brain, and our brain isn't good at complex flawlessly complex logic, right? That's why theorems have to be simple for them to be useful. Proofs don't have to be simple. It's beneficial, but for theorems to be complex is disastrous. It negates the value of verification, essentially, and that's why I bring up that kind of absurd point about. Every implementation is correct if you're not picky about the specification, right? If you allow yourself complex specifications, then every implementation is correct because you just make it its own specification. Now, why don't you make every program its own specification? Just because I want to understand with this more reliably what my program accomplishes, and that's in the theorem, not in the proof. Well, so to me, simple theorems is the most important thing.
Speaking of complex proofs, I feel like so generally I also like to have my proof explicit in front of me, like an Agda explicitly. But sometimes, or when I work out the proof, I generally first do it with pen and paper because I really I come from the math side and I enjoy working with pen and paper. But then when trying to put it like somehow into code, I realized in the Agda, like even in the Agda setting, I'm sometimes just limited. Some things that I can do with pen and paper, I cannot do. Or if I can do them, there's like a very long roundabout way. And I think to some extent, that's where tactics can come in and can like just do this very long roundabout thing that is very clear to you on paper, and it's just like the limitation of the software that hinders you in doing it the way you would want to do it.
Yep. Yeah. Well, so sometimes when we translate from paper to formal and fail, it's because we made a mistake on paper, right? And the paper didn't say, "Hey, you made a mistake," right? So sometimes it's because of that. But you're talking about when it actually is valid, so that you really can generate some maybe very hairy proof, which you would then want to hide, behind your tactics, kind of thing. Yeah. And in that case, I would say, if it's really very complicated, to do it in such a way that it's correct, right? The simple thing you don't know it's correct, and you did on paper, it might be wrong.
Yeah.
You're a good mathematician, so you're better than a novice, but because you're a human, a fair number of them are going to be wrong. All right, so you don't have assurance there. So wouldn't it be nice to have assurance and simplicity rather than assurance and complexity, or assurance and hidden complexity, visible complexity, hidden complexity? Wouldn't it be nice to have assurance and simplicity? And I don't think you'll get there if you use tactics to hide it. That's why you're hiding it, right? It's because I don't want to see this thing, rather than saying, no, I want to see it, stare and meditate on it and take a week and then reflect. And then, I may have to come back in a year because I have no idea or something like that. But, at least you have the reminder there. Yeah. So I think it depends on what you're valuing. And valuing getting to the end of this puzzle, being done and moving on. Or like I'm valuing, it's like meditation or something. I'm valuing getting to the heart of the matter and seeing things I didn't see before.
Yeah.
And it's like sometimes I'm in one space and sometimes I'm in another. I want deep understanding, or I want some outward kind of progress. Unfortunately, right, always really err on the more tick boxes, tick boxes off and move on to the next thing. All of us have that kind of impatience as well on our own, even if nobody's pressuring.
Well, for doing maths, impatience is definitely not a good thing to a property to have or trait to have.
Yeah. And same with science, same with logic and philosophy. Like Galileo rolled balls down inclined planes and dripped water. So 1900 years from Aristotle to Galileo, people believed Aristotle that heavier objects move faster, right? And objects stop moving when you stop applying a force to them. 1900 years later, Galileo said, let's do some experiments. Some inclined planes and rolled balls down. He had to invent a high resolution timer with water, right? And he was very patient. And Galileo's the one who changed, who left the mark on history. He's the one who broke us out of that. What Aristotle said in ancient Greece, about the cosmos as well, the Earth being the center of the universe, all that kind of stuff. So that I think that patience is what pays off, not the impatience. But we live in an impatient culture. We have impatient personalities.
Yeah. I'm gonna stop the stream. I think it was good stream.
Yeah, sure.
Like we can still talk on the call, but like I think that was a good stream. Like we're gonna
yes, thank you.
Continue with this paper next time for anyone who wants to watch us next time. And hope everyone has a good evening.
Well, thank you. Thanks for inviting me, Walter. It was sure good to meet all of you.
Let me just find the button.
And reach out to me. You bet. Yeah, happy to reach out anytime.